Welcome back to a HansonMath.com AP Calculus AB video. This video regards section 4.2, which is straight line motion. Unit 4 is all about applications of the derivative, and here we're talking about straight line motion. A special thank you goes out to Brian Passwater, AP Calculus teacher, for providing these outstanding notes. All right, so one thing we study in calculus or Calc 1 is particle motion, and three equations are going to be important for particle motion. So now might be a good time to pause and write these down. Number one would be position, and a position function is often written as S of t, where time goes in and position comes out, whether that be height or depth or something of that nature. And it's often called S of t, or it could be X of t, which would be position along the x-axis in a straight line, or it could be Y of t, which is position vertically, like along the y-axis, up or down. Okay, so we're looking at straight line motion, which means that you're like on a railroad track. You're not deviating from a straight line, or like think of you're stuck on a rail or on a sidewalk and cannot go elsewhere. Well, what happens if you take the derivative of position? We've talked about the derivative of position would be distance per time, which is velocity. So velocity is the derivative of position. So it could be the derivative of s. Velocity could be s prime. It could be x prime. It could be y prime. Velocity is the first derivative of position. And then if you take the derivative once more, you get acceleration. So acceleration can be thought of as the first derivative of velocity, or it can be thought of as the second derivative of position. Side note that speed and velocity are not the same. Speed is the absolute value of velocity. So in physics, we say speed is a scalar and velocity is a vector. Velocity has a direction, positive or negative. The negative directions would be left or down, and speed strips away the sign. So, you would just say, officer, I was going 75 miles per hour. I'm sorry. If you were heading east, but if you were heading west, you would not say I was going negative 75 miles per hour because they think you're crazy. So the negative could indicate direction, such as east could be positive and west could be negative. But speed, we strip away the sign and we just talk about the scalar. Okay. So we're going to be working with position, velocity, and acceleration. And in Calc AB, all motion, again, is considered straight line motion. Some textbooks call it rectilinear motion, which means motion only happens along a straight path, either horizontally, like along the x-axis, or vertically along the y-axis. And questions involving motion are very, very, very common on the AP exam. So now would be a good time to press pause. If you're watching this on YouTube, a blank copy of these notes will be in the directions. What do you call that? Underneath the video, you'll find them. In the description, there'll be a PDF of these notes if you're on YouTube. So please hit pause, write this all down, and then when you're done, unpause, and I will talk through essentially what's going on. Okay, so we're talking about a bug here. It could be somebody on a skateboard. It could be a cat or a dog walking down a sidewalk. It could be somebody on a moped. It's just some object or thing or particle is moving. So you're going to be asked questions like this a lot in AP Calculus in general and in Unit 4 in specific. So if you are asked a statement, when is a bug stopped, or when is a bus stopped, or a cat, when is it stopped? Something is stopped when it has zero velocity. So the translation for that is velocity is equal to zero. So if you were asked to find when an object such as a bug is stopped, you'd set the velocity equal to zero and solve for t via any number of methods, usually factoring, quadratic formula, or technology. When is a bug moving to the right? Well, moving to the right is defined as velocity is positive. So positive is moving to the right. Think about a coordinate system. Moving to the right is positive. Also moving up is positive. So again, we're going to set the velocity equal to 0, and we're going to use a sign chart or a graph, as we'll look at in subsequent examples today. We defined moving to the left or motion to the left is when the velocity is negative. So negative velocity implies that you're moving to the left or possibly down if it's vertical motion. And again, you do the same thing. You'd set the velocity equal to 0 and use a sign chart or graph, as we will see. How can you tell if an object such as a bug turns around? Well, to turn around, the sign of the velocity would have to change, because if the velocity was positive, it means that you are moving to the right. And then if the velocity flips to negative, that would imply you turned around and were moving back to the left. So turning around would imply a sign change of velocity. How do you investigate this? Well, you'd set the velocity equal to 0 to find out where you have 0 velocity, and then on either side, you'd use a sign chart or graph, as we will see. How can you tell if a car is speeding up or a bug is speeding up? That would be when velocity and acceleration have the same sign. One way to think of this is think about walking in a strong wind. If you're walking to the right and the wind is blowing to the right, that would cause you to speed up, so they'd have the same sign. If you were walking to the left and the wind was also blowing to the left, it's sympathetic, it's helping, so you would speed up to the left. However, if you were walking to the right, but the wind was blowing to the left in your face, it would cause you to slow down, which is the next one. When velocity and acceleration have different signs, you will slow down because the forces are opposite. Okay, think of it that way. If you're walking to the left and you had a strong wind blowing to the right, it's going to cause you to slow down. So when velocity and acceleration have different signs, you will slow down. When they have the same signs, you will speed up. Okay, we will look at all of this in example 1 and beyond. So let's get right to it. Okay, example 1 says, for time between 0 and 8, we don't know if it's seconds, minutes, hours, days. It really doesn't matter. I might say it's minutes just to have something to talk about. So let's say for a time between 0 to 8 minutes only, that's your domain. The position of a bug moving along the x-axis, so it can only crawl left and right along an x-axis, is defined by this function, x of t, which is a position function. If you plug in time for t, its position along the x-axis will be spit out. So time is your input, its x position is your output. Okay, so you plug time in, you get position out. If you use this function, 1/3 t cubed minus 7/2 t squared plus 12t plus 2. Okay, question A, what is the position of the bug when it first starts walking? Well, if you look at the domain, it first starts walking when the time is 0. And since you're given the position function where time goes in and position goes out, you simply plug into this position function, and the bug first starts walking when the time is 0. So that would be the position x at 0 is equal to 1/3 t, which is 0 cubed, minus 7/2 t 0 squared, plus 12 times t, which is 0, plus 2. And of course, 0 times anything is 0. So this zero's out, this zero's out, this zero's out, and you're left with 2, which was the intercept here at the end, which you should know from classes prior than calculus. So at a time of 0, its position on the x-axis is at 2. So if you're thinking about a number line, the bug wasn't starting at the origin, it was starting 2 to the right. So 2 was its initial position on the x-axis. Question B, at what time is the bug stopped? Well, if you look back on your notes, you'll notice that the bug is stopped when the velocity is 0. So you're stopped when the velocity is equal to 0. So we have to find a velocity function, set it equal to 0, and solve for t. So how do we go from position function x to velocity? Well, the velocity is the first derivative of position. So if we want the velocity function, it's exactly equal to the derivative of position. So it's x prime of t. And it will not be hard to take the derivative of this. It will not be hard because it's just a simple series of power rules. So let's do it. 1/3 coefficient times exponent 3. 1/3 times 3 is 1. So you have your 1t. You always subtract a degree. So that would be down to degree 2. Minus 7/2 times the exponent 2. 7/2 times 2 is 7. T, and again, you lose 1 from the exponent or lose a degree. So that would be down to degree 1, which is implied. Plus the derivative of 12t is just the coefficient 12. And finally, the derivative of 2, which is a constant, is 0. Okay, so I'm going to box this in yellow. This is your derivative of x of t, which is now a velocity function. So the velocity function is this. So if I want to know when was the bug stopped, I have to set this velocity function equal to 0 and then solve for t. So this is a quadratic equation, t squared minus 7t plus 12. I want to know what value of t would make this such that it becomes 0. Well, what are our options? We could factor. We could use the quadratic formula. We could use technology. This is a no technology problem, so let's try factoring. So could we split this up as 1 parenthesis times another equals 0? So let's think about it. Let's split up t squared. T squared would be t times t. And then I need something times something, two numbers that multiply to positive 12 and sum to a negative 7. So the numbers that will multiply to a positive 12 and sum to a negative 7 are, you guessed it, -4 and -3. All right. So now using the zero product property, you set each parenthesis equal to 0. So you have t minus 4 equals 0, and you have t minus 3 equals 0. And when you get t by itself, you get t equals 4 and t equals 3. So those are the 2 times when the bug is stopped. The bug is stopped after 3, maybe 3 minutes. And it stopped after 4, maybe 4 minutes. And somebody would say, well, why did it stop? Well, why might you stop? Maybe it's tired. Maybe it stopped for a snack. Maybe it was threatened and endangered and it froze. Okay, so the bug is moving from time 0 to 8. And during that 8-minute interval, it decided to take a break at exactly the 3-minute mark and the 4-minute mark. All right. Next, on what intervals is the bug walking to the left? Well, if you use your notes above, walking to the left is when the velocity is defined as negative. So left is when the velocity v of t is less than 0, aka negative. Well, how to do this? The best way that we have come up with as calculus teachers is to make a sign chart. So I'll make the sign chart like the following. Let's draw a number line. And you don't have to necessarily label all these different points. But since our domain here is from 0 to 8, let's say minutes, 0 to 8, I'm just going to put little tick marks and I'm going to capture every integer from 0 to 8 like this. Okay, you don't necessarily have to be this detailed, but 0 to 8 is such a small range of numbers that I don't think it'll hurt. Okay, so that'll capture our whole experience of the bug's travel in terms of time on the domain 0 to 8. Now, the first most critical thing to put in is the times at which the bug was stopped with a velocity of 0. So I'm going to note that this chart is keeping track of the signs of the velocity v of t. Okay, so far I know from part B that the bug was stopped at 3 seconds and 4 seconds. So I'm going to plot a point on we were saying minutes, on 3 minutes. And I'm going to note that its velocity was 0, meaning it was stopped there. I'm also going to plot a point at 4 minutes and note that the velocity was also 0. Those are the only two places where it was stopped, or those were the only times where it was stopped. Okay, every other point on the timeline, it was moving. Now, which way was it moving? Well, the bug has the ability to walk either to the left or to the right. That's all it can do is stay on a track and walk left or right. But unless we investigate the signs of velocity, we really don't know. Was the bug walking to the right and then it caught its breath at the 3-minute mark? Or was it walking to the left? Did it continue in a straight path? Was it going nothing but right, right, and right? Or was it going to the right for a little while and then it decided to turn around and head back this way? We don't know until we investigate the sign chart. But thankfully, we do know, since you have to undergo a sign change to turn around, and you can't turn around without having 0 velocity, if only for a second. So I'm going to color code this. We know for sure that from 0 up to 3, it was only heading in one direction, either left or right. At the 3-minute mark, it could have continued to go to the right, or it could turn around and go to the left, because when it has 0 velocity, it stopped. When it stopped, it could continue to go one way or it could turn around. So I'm going to switch to pink. From 3 to 4 minutes, it may have turned around or it may be going the same direction. And then after it also stops at 4 minutes, it could keep going the same direction, or again, it could turn around. But from 4 to 8 minutes, it can't turn around again because it doesn't undergo a stop or a 0 velocity again. So really, to do this sign chart to figure out where it was walking to the left, I have to pick a test point. I have to pick one test point between 0 and 3. I have to pick another test point between 3 and 4. And then I have to pick a final test point between past 4 and up to 8, so that we can look at the sign, and the sign will tell us if it was moving left or right. When we plug into the velocity function, negative indicates walking to the left, positive would indicate walking to the right. So let's do some side work and figure this out. So let's first go in this red section. Which way was the bug walking? Well, I'm going to choose to pick a test value of 1. So that would be V of 1 is equal to, we're plugging into this velocity function, which I circled in yellow. So that would be 1 squared minus 7 times 1 plus 12. Okay, if you simplify that, you end up with positive 5. And we don't really so much care that it's 5, but we care that it's positive, because positive velocity unequivocally means you're walking to the right. So the bug was walking to the right from 0 to 3 minutes or seconds. Again, we don't have units here. Okay, we know that beyond a shadow of a doubt. Now, what happens between time 3 to time 4? The bug could continue walking to the right. It just momentarily stopped, or it could turn around. We don't know unless we pick a test point. So let's pick a test point between 3 and 4. How about right here at 3.5? So again, some side work. The velocity at time 3.5 would be equal to, okay, use your derivative here, x prime, which is velocity. That would be 3.5 squared minus 7 times 3.5 plus 12. Okay, what does that come out to? Well, I don't have a calculator in front of me, but when I did this earlier, crunch it out for yourself. You end up with a negative. Okay, you get a negative something. And the fact that it comes out as negative, and we're talking about velocity, negative velocity means that the bug or the object is moving to the left. So now we know beyond the shadow of a doubt, the bug is moving to the left between time 3 and time 4. Okay. But we don't know past time 4 if it continues going to the left or again, if it turns around when it was stopped with a velocity momentarily of 0. So again, we need one more test point. Okay. Anything in this green area will do. I'm going to pick 5. So again, some place where I have space for some side work, I'm going to do V of 5 is equal to 5 squared minus 7 times 5 plus 12. Well, that one's easier for me because there's no decimals. 5 squared is 25. 7 times 5 is 35. 25 minus 35 is negative 10. Negative 10 plus 12 is positive 2. Again, I don't care about the 2 so much, but I care immensely about the positive. The positive velocity means we're moving to the right. So in this green section, the bug is moving back to the right. So if we're thinking about a story of the bug's journey, the bug started 2 units from the origin. It walked to the right from 0 time, 0 minutes, 0 seconds until 3 seconds. It turned around and walked to the left from 3 seconds to 4 seconds. And then it turned around again and walked to the right from 4 seconds to 8 seconds and stopped its journey. Okay, again, I keep switching between minutes and seconds because we were not told units, so the time could be whatever you want. But that's how you interpret the problem. The sign of the velocity tells you what's happening. Negative velocity is movement to the left. Positive velocity is movement to the right. And exactly 0 velocity means you are stopped. Okay, so I hope that was a clear problem, and I hope that one helps. Okay, I'm going to quickly pause, and then we'll start on example 2. Okay, one side note, back to example 1C for just a minute. I forgot to write the notation for what intervals is the bug walking to the left. It was walking to the left between time 3 and 4. So the best way that you'll see on the AP test to write that is it's walking left on the interval. Okay, this is how I like to write this. It was the time was less than 4, but it was also greater than 3. So this compound inequality is the best way to write the interval during which the bug was walking to the left between time 3 and time 4, just like that. Okay, now we'll move on to example 2, which is a good one. Example 2 gives you a graph. Okay, and the first thing I want to note is the graph depicting position or velocity or acceleration? You have to be very sure or else you can't move your knowledge forward. Okay, so I'm going to start reading here. Example 2 says, the graph below models the velocity. So we're literally looking at a graph of V of t. I would note that on my paper. And we're on the time interval. Again, we don't know seconds, minutes, hours. We weren't told. But the time interval is inclusive of 0 all the way through, including 13. But we're looking at velocity. So here's how you could turn this into a story. The bug, we're talking about the bug again. The bug starts at time 0 with a velocity of 0, which means it's stopped. Now, the velocity is positive and increasing. So that means it's moving to the right. How do I know it's moving to the right? Because the velocity is positive and it's also speeding up. How do I know it's speeding up? Because the velocity is literally going up or increasing. So it's moving to the right and speeding up. At 3 seconds, we'll say 3 seconds, it's still moving to the right, but its velocity is not increasing. The velocity is constant. At 6 seconds, it's still moving to the right because we're in the positive y values. We still have positive y values, so it's still moving to the right, but it's slowing down because we're approaching a velocity of 0. So when the slope here of velocity is negative, it's slowing down and heading to a velocity of 0. And now we're switching from positive velocity to negatives, so it turned around. So now in these negative velocities, the bug turned around and is heading left. It's heading left and actually speeding up because the magnitude of the velocity is getting bigger. But once we get to 10 seconds, It's slowing down, but it's still moving to the left because we're in negative velocity land. But it's slowing down and going back to a velocity of 0, which means once again it's stopped at 12 seconds. What happens after that, we're not privy to because the graph literally cuts off. All right, so since this is tracking velocity, so if you're thinking about it as x comma y or domain and range, the input is time and the y coordinates are velocity. The y coordinates are literally velocity. Okay, so the velocity is positive and increasing, positive and constant, positive and decreasing to 0, and then negative, which means it's moving to the left, but it's speeding up, and then it's slowing down, but still moving to the left, and then stopped. Okay, that's how you read the velocity chart or graph. It's really a graph. If you want to go back and check it out again, please do so. Okay, question A, what's the velocity at time 3 and at time 11? Well, since the velocity is the y coordinates, you're just reading the y coordinates given the x coordinates of time. So v of 3 would be over 3 up to 6. So it's a velocity of 6. And v of 11 would be the velocity at time 11, which would be over here. At 11, we're at the velocity of -1. Okay, so that's straight off the graph because the graph is literally depicting velocity. All right, well, what about question B? Question B is asking about acceleration. So what's going on there? Our graph is a graph of velocity. How do we go from velocity to acceleration? Well, if you look back in our notes and what we've talked about, to go from velocity to acceleration, you have to take the derivative of velocity. So acceleration A of t is literally equal to the derivative of velocity. And if we're looking at this graph where the y values are the velocities, to go from y values of velocity to v prime, the derivative of velocity, you're not looking for the y coordinate, but rather you're looking for the slope. So I'm just going to put in English here. We need to look at the slope of v to get v prime, which is also known as acceleration. Okay? So if v is the velocity, which is literally the y coordinates, v prime is the slope of the velocity graph. So to find a of 1, a of 5, a of 9, we have to look at the slopes of the velocity graph. So a of 1 would be v prime of t at 1, which is the slope of v. So the slope all in here is up 2 over 1, up 2 over 1, up 2 over 1, which is a slope of 2. So your acceleration is 2 at 1 unit of time, 1 second. Okay, what about a of 5? Well, at 5 here, your slope is 0. It's flat. Your slope is 0 all in here, which means no 0 acceleration. You're not accelerating. The velocity is constant. So a of 5 is 0. And then finally, a of 9. At 9 here, your slope is down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1 is -2. So again, if velocity, the graph of velocity, the y coordinates tell you velocity, the slope of the v graph is v prime, which is acceleration. Okay? I hope that makes sense. All right, part C. Part C says, okay, let me clean this up a little bit. Part C says, at what time does the bug turn around? Well, if you go back into your notes, the bug turns around when the velocity undergoes a sign change. Okay, so where does the velocity undergo a sign change? The velocity from time 0 all the way to time 9 is all in the positives. And then the velocity switches to the negatives from time 9 to time 12, all the way here it's in the negatives. So where does the y values flip from positive to negative? Right here at 9. So we know this is where the bug changes direction. Okay, so it turns around or changes direction at t equals 9 because v of t changes sign from positive right here to negative, from positive to negative. Okay, that's your reasoning. Got to be very specific. You can't be too specific in this course. The velocity changes sign from positive to negative at time equals 9. All right, next question, D. On which interval does the bug have a negative acceleration? Well, negative acceleration is when the following would happen. Let's make a little illustration here. Acceleration, A of t, acceleration is the same as v prime. Okay, so we're looking when acceleration or v prime is less than 0, because less than 0 is negative. Well, if you think about what we talked about earlier, we said to find v prime or to see v prime, you have to look at the slope of v. To have v prime, we have to look at the slope of v being negative. So what does negative slope look like? Negative slope is downhill. So this v of t graph has negative slope from here all the way to here. So you have negative slope from a time of 6 all the way to a time of 10. So it has negative acceleration when t is less than 10, but greater than 6. Okay, how do we know? Because that is when v prime of t is less than 0. That means the slope is negative. That's how you read that. V prime of t is the slope of t. It's when the slope is negative, like you're sledding downhill. All right, and finally, part E is a little bit of a tricky question. It says, how many times is the speed of the bug equal to 2? Well, we're not really given the graph of speed per se. We were given the graph of velocity. So once again, this is v of t, which is depicting velocity. So speed is a velocity, but you strip away its sign. Okay, so we have a speed or a velocity of 2 here. Okay, this is velocity of 2 here, and you also have a velocity of 2 here. But remember, speed is the absolute value of velocity. So the velocity could also be negative 2, and the speed would just be 2. Well, you have velocity of negative 2 right here. So since speed is the absolute value, it could be plus or minus 2. So you have speeds of 2, which means velocity of 2 or negative 2, here, here, and here. So how many times is the speed of the bug equal to 2? 3 times. So, and what are those times? That would be when t is 1, 8, and 10. Let's double check that at time 1, 8, and 10. That's correct. Okay, so here were some questions graphically involving velocity, acceleration, changing direction, acceleration, and speed. So I hope those are good examples and they make sense. You can always go back and watch again. Okay, so now we'll erase and we will go to question example 3. Okay, example 3 is extremely calculator active, meaning you're going to want your TI-84. That's what I'm going to do this demonstration on. This is based on TI-84. It says just in the small time interval, just from 0 to 2, that's your domain, from 0 to 2, a bug is moving along the x-axis with a velocity. This is a velocity function. We're starting with a velocity function at equal t squared times sine of t cubed minus 1.5t. Okay, you were given the graph here on this note sheet, but what I'd like to do is I'm going to switch over to my trusty TI-84, and we're going to go through this on there. And I will write down the questions on my screen, and we'll go through them so we don't have to flip back and forth. So this will also be a tutorial on how to use the TI-84 to do some calculus. Okay. Question 1A is find the acceleration at time 0.7, A of 0.7, and then is the bug speeding up or slowing down at that time? Explain your reasoning. All right, so the next thing we're going to do is we're going to plug this function into the TI-84. So at this time, I'm going to switch to my TI-84 screen. And this should be the correct function. So if you need to pause and type this into Y1, please do so now. Okay, you can pause. We're typing in, again, the TI-84s don't use T, you use X. So that's this button right here. Okay, X. So you've got, instead of T squared, we have X squared times sine of X cubed minus 1.5X. Again, we're using X instead of T. Okay, if you need to pause, please do so. And the other thing I will mention is in calculus, you need to be in radians. Okay, so I'm gonna go back to this. I just hit delete by accident. Whoop, that's not it. Okay, sorry about that. I inadvertently deleted my function there. So there it is again. And as I was saying, you want to always make sure for calculus you're in radian mode. So on the TI, I'm going to hit mode and double check that I'm in radians here and not degrees. Again, you don't want it flashing on degree. You want it blackened in on radians. So I'm going to hit enter, and now I'm confident I'm in the correct mode for doing trig functions. So I'm going to go back to y equals. That's our function here that we're going to be answering questions on. And I usually like to start with a 10 by 10 window. So that would be zoom standard, which is zoom 6. Zoom 6 is zoom standard. So if we look at that, that's what this function looks like. But keep in mind on your worksheet, for example 3, it says the time domain is only from 0 to 2. Okay, we have a lot of extra superfluous information here that has no bearing on the story. So in that regard, I'm going to go to window and I'm going to change the X min to 0 and the X max to 2. That's our time domain. We only need to look at the bug from time 0 to time 2. That's it, period. So now if we go back to graph, we just see this. This is the pertinent part of the graph we need to look at. But also notice that we have a lot of dead space. Our Y values don't appear to really be any higher than about 3. And we really don't need to see anything lower than about 3. So I'm going to go back to window and I'm going to make our Y min and max. I'm going to make the Y min -3 because we don't need to see any lower than that. And I'm going to make the Y max 3 because we don't need to see any higher than that. So now if we go back to graph, we get a really good close and critical look at the velocity of this bug. And it really fills up the screen nicely. Okay, so one thing I'm going to note here on my screen is I'm going to just put a little note to myself that we're looking at V of t. All right. So if you wanted to find out some velocities of the bug, my good people, you could just do this. This is the best way, in my opinion. You could hit trace, and then you can plug in 0, and then hit enter. So that means at time 0, when the bug is just starting to keep track of time, its velocity is 0. If I want to know its velocity at 1, I would hit trace 1, enter. Its velocity is negative, which would mean it's moving to the left. If I were to hit trace 1.5, enter, at 1.5 seconds, or when the time is 1.5, the velocity is just over 2, which means it's moving to the right because 2 is positive. So when you plug in x values of time, it spits out y values of specific velocities. Okay, so the bug here is moving to the left because these are negative velocities. It turns around right here where I'm wiggling the mouse. Then it starts moving right because these are positive velocities. And where I'm wiggling the mouse, it turns around again because then we go back to negative velocities. Okay, that's how you read this. So on your worksheet, I'm going to write on my screen here. I'm going to switch to red. And I'm going to just write part A asked us because it doesn't help me to flip back and forth. Part A says, first find the acceleration at time 0.7, A of t. Well, keep in mind, we're not looking at a picture of acceleration. We're looking at a graph of velocity. So you have to be able to translate, how do you go from velocity to acceleration? Well, you'd have to take the derivative of velocity to get acceleration. Okay, so if we want to answer questions about acceleration, we don't want to look at v, we want to look at v prime. V prime is the derivative of v. So we literally need the derivative of v. And lucky for us, the calculator has that ability. To do the derivative, you're going to do the following. On your TI calculator, while you're still in this graph, you're going to go to second trace, which is the calculate menu, second trace. And since we want the derivative to go from v to v prime, the derivative is option 6, dy dx. So option 6, if we hit 6, we can tell the calculator to find the derivative wherever we want. We want the derivative at time 0.7. So I literally typed it in, 0.7, and then you hit enter. And you should see this. Okay, we see that at time 0.7, the y coordinate here is the velocity, and the derivative dy dx is the acceleration. So our acceleration at time 0.7 is negative 0.9205. I'm going to go to 4 decimal places. Okay, everyone knows the rules for College Board. You need at least 3. 4 would be safer at this point. So if we think about this, our y value is velocity. Our velocity is negative. Our acceleration is negative. So since they're both the same sign, it actually means the bug is speeding up. So now we know that it's speeding up at time 0.7, which that actually answered the second part. Since we know that the acceleration is negative, the velocity right here at the same time is negative 0.3182. Since the signs are the same, we know that's speeding up. So we could say speeding up since, or because, v of 0.7 and a of 0.7 are both negative. Okay? When the signs of velocity and acceleration agree, that means that the object or the bug is speeding up. Okay, that is our reasoning. That is part A. All right. So I'm going to erase this due to not cluttering the screen too much. And we'll talk about part B. Okay, part B on your note sheet says, find any values of t just in the interval time is greater, less than or equal to 2, and also less than or equal to 1. So just in the interval between 1 and 2 inclusive. When is the bug at rest? So it's at rest when it has a velocity of 0. So rest implies that the velocity is exactly equal to 0. And remember, this is a graph of velocity. This blue curve is literally tracking the velocity. Okay, so you would have 0 velocity right here and also right there. Okay, so how can you find those using the technology? Well, there's 2 ways. You could either use the 0 finder in the calculate menu, but I found students have had more success doing the following. if you go back for a moment to y equals, let's go back to y equals, hit y equals, leave y1 as it is, and go down to y2 and set that equal to 0, meaning it'll draw a line where the velocity is 0. So if we hit graph, now we have our blue velocity function and a straight line in red that indicates where the velocity is 0. So where they intersect, you literally have a velocity of 0. So the bug has 0 velocity here and here. Now, since they intersected, you can literally use the intersect feature, which I think is easier for most students. So to use the intersect feature, you go into the calculate menu, which is second trace, and the intersection is choice 5. So I'm going to hit 5. It asks for first curve and second curve. All you need to do is hit the right cursor and move the blinker close to the intersection by eyeball. So that should be plenty close enough. And then you just press enter 3 times. Enter, it says second curve. It automatically puts it on there for you. Enter, guess, enter. So there we go. Okay, the intersection where the velocity is 0 is at time 1.2247. Okay, so I'm going to jot that down, document our work. Okay, the velocity is 0 when the time is 1.2247. Again, we weren't given units, so I don't know if it's minutes, seconds, hours, or what have you. But there's another point in time in which this happens. It also happens down yonder right here. So to do it, we just have to repeat the process. You got to go into the calculate menu, second, trace, intersect, which is 5. Move your blinker using the right cursor to the time further down yonder. Okay, right about there. That's plenty close enough. Hit enter. It automatically moves the blinker to the second curve for you. Enter and guess. Simply hit enter. And there it is. That's your second time when the velocity or the y value is 0. So the velocity is also 0 when the time is 1.8011. All right. So to me, that's my preferred way of using the technology to find what time is the velocity 0. Okay, so we have 2 different timestamps there. I'm going to leave that up because we're going to have to reference that for question C. Okay, question C, I'm going to switch to dark red color. Okay, this was question B from the notes. Question C, I'm going to put right here. It says, find the open intervals from 0 to 2 when the particle is moving to the right. So we know by definition, the particle is moving to the right when the velocity, v of t, is positive, which means greater than 0. That's when it's moving to the right. Well, if we trace this in yellow, these velocities are all below 0. So these are all negative. These are all negative velocities, all in here. And then at this point, it flips to positive velocities. So the velocity is all positive during these time frames. And then it switches back to negative right here. These are negative velocities. So the only positive velocities of the bug are in my orange section. And in part B, we figured out where those points are. This point is at 1.2247, and this point is 1.8011. So it's moving to the right between those two. So we'll say it's moving to the right when the time is less than this one, 1.8011, and when it's greater than this one, which is 1.2247. Okay, so the bug is moving to the right when the velocity is positive, meaning above 0 or greater than 0, all in this interval. Okay. And then finally, I'm going to erase to do part D. Part D says, Find the acceleration of the bug when the velocity is -1. Okay, so we first have to find when is the velocity -1. So we need to find the time when the velocity v of t is equal to -1. And again, just to be super clear, this blue curve is tracking the velocity. Okay, so we need to find the time first when the velocity is -1. So the best way in my mind to do this is to go back to y equals and change your y2 to where the velocity is 0. Now change it to we want the velocity is -1. Okay, that'll show us everywhere when the velocity is -1. So I put in a -1 for y2, and I'm going to go back to graph. And now that shows me everywhere the velocity is -1. So where does the intersection occur? We end up with an intersection right here. Okay, that's the only time along the bug's travel that its velocity is precisely -1. So how do we find what time this corresponds to? Well, we have to use the intersection feature and figure out what time that is. So again, this is second, trace, intersect, which is 5. Hit the right cursor to move your blinker way to the intersection when the velocity, the red line, the velocity is -1. Okay, that's plenty close right there. And then we power through with enter once, enter twice. Guess you hit enter last time. So there it is. When the velocity is -1, the time is this. So the time is 1.8368. Okay. That's when the velocity is -1. So the final part of this, it says find the acceleration at that time. So now we need to find the acceleration when the time is 1.8368. Okay, so to do that, again, if we're looking at a graph of velocity, to get to acceleration, we have to find v prime, which is the derivative. So v prime is the derivative. So I'm going to go to second, trace, which is calculate menu, dy dx, which is derivative, option 6. And I want the derivative at the time 1.8368. So I'm going to literally just type in 1.8368, enter, and there it is. Okay, that will give you your derivative, which will be acceleration. And mine's partially obscured right here, so we'll write it down. The derivative here is -28.8722. So look at all the good information that the calculator gives you. X is time, so at a time of 1.8368, the velocity is y, -0.9978. And the derivative, which is the acceleration, is -28.8722. Since the sign of the derivative and the sign of the velocity are both negative, that would mean the bug is speeding up at that time, just as an FYI. Okay, so that was a lot of information there regarding acceleration and speeding up and velocity, and a lot of information on how to use the TI-84, so I hope that helped. That was example 3. Okay, I'm going to pause for a quick sec, and we'll knock out example 4. Okay, for example 4, we are away from the calculator. We're back to our note sheet because we are looking at a table of information. So example 4 says, from a time domain of 0 to 8 inclusive seconds. Now we finally have units here. Now we're in seconds. All right. Not a bug, but some particle, maybe like a electron, I don't know, moves along the x-axis. The position, velocity, and acceleration of particle P are differentiable and modeled by the functions x of p, v of p, and a of p respectively. Now remember, differentiable implies continuous. So these are also continuous functions that will come up later. Selected values for x, the position function, v, the velocity function, and a, the acceleration function, are shown in the table where x of t is measured in meters. Okay, so in this function for x, so let's see, x of t is going to be seconds go in and meters come out. Okay, so this is position in meters. The velocity function would be velocity, which is in meters per second. And the acceleration function is a rate of a rate, so it would be meters per second. And a more succinct way to write that would be meters per second squared. That's just some side work where I'm thinking about the units. Okay, so the units, the position would be meters, the velocity would be meters per second, and the acceleration would be meters per second, or meter per second squared. And I'm going to double check. It is meters and seconds. Okay, the time is all in seconds. Question A, is the particle P moving towards or away from the origin at time 4? Give a reason for your answer. Okay. So if we draw a little number line like this, woo, okay, I'm going to put 0 in the middle for the origin. This is the origin. Okay, it says, is the particle moving towards or away that origin when time is equal to 4? Well, let's look in the table and let's see, where is the particle at time 4? When t is 4 right here, its position is 6. So at time 4, it's at position 6. 1, 2, 3, 4, 5, 6. Okay, it's here. So this is its position at t equals 4. So now, at that time, is it moving towards the origin or away? So I'd need to know, is it moving right, away from the origin, or is it moving left, towards the origin? Well, how do we determine left or right? Left or right is determined by the sign of the velocity. So if we look at the velocity row here, at time 4, the velocity is -1. So a velocity at 4 equaling -1, the negative means it's moving to the left. So at this time, at time 4, it's over here at 6, but it's heading left. So since it's heading left, it is indeed heading towards the origin. Okay? So we know it is heading left for sure towards the origin. So the answer is yes, it is heading towards the origin for the following reasons: that the velocity at time 4 is -1, which means it's heading to the left. Okay, so for the work I have shown, part A, it is moving back towards the origin, yes, because it's moving to the left from a position of 6. Okay, part B says, is the particle speeding up or slowing down at time 7? Well, if you go back to your notes, we said that speeding up and slowing down. Let's start with speeding up. Speeding up is when velocity and acceleration have the same sign, just as a recap. And slowing down is when the velocity and the acceleration have opposite signs, because it's like the forces are fighting each other. Okay, opposite signs. Well, let's take a look in the table here. Let me erase. Let's see what in the heck is going on at time 7. So at time 7, the velocity is negative. So I can put the velocity at time 7 is -4. And the acceleration at time 7, the acceleration of particle P at, I guess it's the velocity of particle P2, that's its name. The velocity of particle P at time 7 is -4. The acceleration of particle P at time 7 is -3. And they have the same sign. So the fact that they have the same sign means that the particle is, you got it, speeding up. And that would be your evidence right there, that V and A have the same sign. Speeding up. Because the forces are sympathetic. They're not fighting each other. It will be like if the wind was at the back, at your back, it will be helping you along. Okay. Part C. Part C, I got to move up, so we're not going to be able to see the table, unfortunately. Part C says, use the data in the table to approximate VP of 2. Indicate units of measure. Okay. So let's see. V of particle P, that's the velocity. Notice in the table, I think I'll do this. I'm just going to put part C right here, and it's going to say estimate the velocity of particle P at 2. So we can look at the table. There is no time value of 2. Okay. We're not privy to that. There is no time of 2. So how do you estimate a velocity? Well, velocity is position divided by time, or distance divided by time. So to estimate, we're going to have to look on both sides of 2, which would be here and here, right? So since velocity is change in position over change in time, that the best that we could do is we could do the velocity at 3 minus the velocity at 1. That's the change in, excuse me, that's not right. We have to do change in position. So that'd be x at 3 minus x at 1. That's the change in position in meters over the change in time, which would be 3 minus 1, because 2 is captured in that interval. Okay, so this is literally change in x, which is meters, over change in time, which is seconds. So meters per second is your velocity we're looking for. Okay, so if we keep going with this, the position at 3 is 8 minus the position at 1 is 2 over 3 minus 1 is 2. So that's 6 over 2, which is 3. So the approximate velocity at time 2 is 3 meters per second. Okay, so keep in mind that the velocity is meters per second, which is a change in position x over a change in time t. It's got to be like that. If we would have done velocity divided by time like I errantly started, that would have been acceleration. Acceleration is velocity divided by time. Velocity is distance divided by time. Okay, so that was part C. Part D, which I'm going to put over here in dark red. Part D says, is there a time between 1 and 7 seconds such that the velocity of particle P is 0? Is there such a time where that has to be true? Well, if we take a look, if I highlight in yellow the row for velocity, we're looking at all of this. Okay. So at the beginning of the time interval, we have a velocity of 5. Then the velocity reduces to 2. And then the velocity reduces to -1. Well, they told us that this function is differentiable, and differentiable implies continuity. To be differentiable, you have to have continuity. And if you're continuous, you can't teleport from 2 to -1 without going through 0 somewhere between 3 and 4 seconds. If you remember from an earlier unit, that is called the intermediate value theorem. Okay, so the answer to this is yes, due to the intermediate value theorem. Okay, so we know that the interval from 1 to 7. So we know the interval from 1 to 7 is continuous because we were told it's differentiable. Okay, we were told it's differentiable, which implies continuity. So, due to the intermediate value theorem, since we know at time 3, the velocity is 2, and then at time 4, the velocity is -1, there must be some time C where the velocity at that time is 0. Okay, this is all due to the intermediate value theorem. Again, you can't teleport from a velocity of 2, which means it's going to the right, to a velocity of -1, means the particle is going to the left. It's continuous. So due to not being able to teleport, you can't go from a positive velocity to a negative without going through 0, which is what the intermediate value theorem states. So that's a throwback to, I believe, Unit 1. Okay. And finally, we'll tackle question E. Question E says the following. Okay, again, this is all on your worksheet, which is downloadable in the description. Question E says, for a time between 5 seconds and 8 seconds, there's a new particle Q, not P, but a new particle Q moving along the same axis. The position of particle Q is modeled by the position of particle Q is given by 12 minus t minus 10 quantity squared, like that. It says at time t, when t equals 7, are the particles moving towards each other or away from each other? From each other at time 7. That's what the question asks. Well, let's first find out. And what I'm going to do is let me have some free space here to write. Okay, and again, this is part E. Let's first do the following. Where are the particles at time 7? Where are they? So it said that we're only looking from times 5 to 8. Okay, that was the stipulation of this problem. So I'm going to start a number line, and I'm just going to go 5, 6, 7, 8. That's all I need because it was a restricted time domain. It says at time 7, where are the particles at time 7? Okay, so let's find out. At time 7, this is actually not the way to do this. Okay, let me get rid of this. So at time 7, this is what we have to find out. We have to find the position of particle P at time 7. So at time 7, particle P is at 5. So I'm going to go like this. I'm going to say it's at 5. Okay, 5, 4, 3, 2, 1. And then I'm going to make a dot here. Okay, particle X at time 7 is at 5. So it's here at 5, and I have to put this timestamp. That's at time is 7. That's how you do this. And then let me switch to pink. Where is particle Q at that time? Well, particle Q is governed by this new formula here. So particle Q's position at time 7 is 12 minus, we're going to replace T with 7 minus 10 squared, which is 12 minus 7 minus 10 is -3 squared. So that's 12 minus -3 squared is 9. 12 minus 9 is 3. So at time 7, particle Q is at 3. So it's here, okay? So this is particle Q at time is equal to 7. It's at 3. And particle P is at 5 at t equals 7. Well, at that time, at 7 seconds, are they multiplying? Are they moving closer to each other or away from each other? Well, to look at that, we'd have to look at the velocity. So for particle P in green, that was given in the table. So the velocity at 7 seconds, the velocity of particle P is -4. And a -4 means that it's moving to the left. So particle P is moving this way to the left. Okay, how do I know that? Is because at 7 seconds, particle P was at 5, and it's moving negative velocity, which is left. Okay, so we've got that figured out. But what about particle Q? Its position at time 7 is at position 3, so it's to the left of P. But which way is it heading? Well, to know that, we need to look at the velocity. So how do you look at the velocity when they gave us a position function? Well, you guessed it, to go from position to velocity, we'd have to take the derivative. So we need to look at the velocity of particle Q at time t is equal to x prime of t. If we take the derivative of this 12 is 0 because it's a constant. It's gone. And now we'll use the chain rule. So we have a negative. We take our 2 and bring it in front. We keep the inside function alone. Don't touch it. The power decreases from 2 to 1, which is implied, times the chain rule. The derivative of the inside is 1, which doesn't do anything. So now we need to figure out what is the velocity at time 7. So that'd be x for particle Q prime at time 7 is -2 times 7 minus 10, which means -2 times 7 minus 10 is -3. And -2 times -3 is +6. I don't really care about the 6, but I care immensely about the positive, because positive velocity means it's moving to the right. So particle Q is moving to the right. So since particle Q is at 3 moving right and particle P is at 5 moving left, they are indeed moving towards each other at that time. Okay, all of this is your reasoning, all of the work. So finally, to answer the question, I would say yes, particles Q and P are moving towards each other. Okay, and all the reason why is documented in the work below. Okay, so we learned a lot in this lesson. The salient points are an x of t function gives you position, a v of t function gives you velocity. Velocity positive means you're moving right, negative velocity means you're moving left, and acceleration is the derivative of velocity, which could be the slope of velocity if you're looking at a graph. So a lot of good information. This is kind of a tedious lesson, but it's a good one, and the motion information doesn't go away. It's all over the AP test. So I hope this video helps. Thank you for watching another HansonMath.com AP Calculus video, and we'll see you on the next one. Good luck, and thanks a lot.